So I like to talk about this cohomological Hasse principle and also its applications. So this is a plan of my talk. So first, I talk about this what cohomological Hasse principle means. Yes. And then second part is application to the motific cohomology group. And third part is another application to the special value zeta function. So this part is friendly to the number theories, number theorist. And the final part is application to the resolution of singularities. So this part is supposed to be friendly to the Algebraic geometers. Okay, so let's recall the cohomological Hasse principle. So I like to start with a very, very classical fundamental fact from the number theory. So which is the Hasse principles for the quadratic form. So you're given some quadratic form in a variable with rational coefficient. So this equation has a non-trivial solution in Q, field of rational, if and only if it does in the real numbers and also all periodic numbers for all primes P. So this is a very, very classical fact from the number theory due to Hasse and Minkowski's. And then now in the proof, n equals 3 is the most essential. Okay? And this case has cohomological interpretation, which looks like this. So this works over any field, and given this quadratic form of the 3 variable over this general field K, so this equation has a non-trivial solution in this given field K if and only if this so-called this symbol AB vanishes in the second Galois cohomology of this field K with coefficient in V mod 2. So this existence of the non-trivial solution for the quadratic form is somehow controlled by the second Galois cohomology of the field. Okay, then with this interpretation, now Hasse principle, original Hasse principle is now equivalent to the injectivity of the map from the second cohomology of the Galois cohomology of the Q going into the direct sum of the second Galois cohomology of the QP and also R. Okay, that's the due to this cohomological Hasse principle. And then we have another input, which is a residue isomorphism, which equalizes the second Galois cohomology of the QP to the first Galois cohomology of the F field, finite field, which is a residue field of the QP. And with this extra input, the original Hasse principle is now equivalent to the injectivity of this map here. So going from the second cohomology of the this Q into direct sum, this is the main part. This is the main part. Direct sum of all primes, rational prime P, of the first Galois cohomology of the finite field. And also we have the second Galois cohomology of the real numbers. So now, first generalization of this is given as follows. So let's X be a spectrum of the integer ring of the number field, or its geometric analog, namely the smooth proper curve of a finite field. Okay, so with function field capital K. So we are either in these two cases, then as a generalization of the previous map. Well, now just for simplicity. So I don't want to be bothered by this real numbers. So I mean, just for simplicity, we assume there's no map from a spectrum R to the X. So which is equivalent to say we are either in this. We are either in this geometric case, or we are in this case with K totally imaginary. Okay, so that's the assumption here. And then we, as a generalization of the previous map, we consider this map. Going from the Galois homology of the second Galois homology of this global field capital K into the direct sum here, this is a set of the cross point, which is equal to the set of the finite places of this global field. And this one is a residual field. So this one is the first Galois homology of the residual field of this point X, which is finite field now, okay? So this is a generalization of the previous complex. In case of K is a rational, so this coincides the previous complex, but this second Galois homology of the real numbers are removed. But we neglect it here, okay? Just for simplicity. And then remark is, okay, so also this coefficient is just in like nth root of unity. In case, characteristic of K is prime to n, and otherwise, I don't want to go into detail. But anyway, point is now, this second Galois homology of this global field capital K is Brouwer group. This is an isomorphism class. This is a group of the isomorphism classes of the central simple algebra of this global field K. And this means n torsion part, okay? So in conclusion, this classical result, this is due to Hasse and Netter and Brouwer. Hasse principle for the central simple algebra over the global field is equivalent to the injectivity of this map here. Okay, so that's all these things are classical, very classical from number theory. Okay, now we'd like to talk about this generalization of this fact to the higher dimensional situation. So this is the cohomological Hasse principle in a higher dimension. So we consider now X scheme of finite type of a finite field or integering, rational integering, okay? Usually this kind of schemes is called arithmetic schemes, okay? Then Kazuya Kato introduced some complex, which is now called the Kato complex. So for the fixed integer n, so this is a Kato complex of X with coefficient in Z mod n, okay? This looks like this. So degree A term, okay, degree A term is a direct sum over the set or the point of this X whose closure in X has dimension A. So which means the transcendent degree of the residual field of this point is A over finite field. This is the characteristic P case, or transcendent degree of the residual field is A minus 1 over the Q. This is the case of the characteristic 0. So because we are talking about the higher dimensional schemes, there are many points like this, okay? And so degree term in degree A of this complex is this direct sum over this set of the Galois homology in degree A plus 1 with this state twist. So this state twist is just like a twist of this sheaf or Galois homology of the nth roots of unity. Okay, so this is the degree A term, degree A minus 1 term. So it goes on until the degree 0 term, where the sum is over a set of the close point. This is a close point. Dimension 0 point means close point. And then this terms H1 of this residual field, which is finite here. Okay? And this is a Galois homology finite field. It's not so big. This is a finite group. But all other terms are infinite group. So all these terms are infinite direct sum of the infinite groups. So it's very large groups, okay? And a really large complex. Okay? And then we define some very important invariant associated X, which is now called a Kata homology. So this is defined as a homology of this complex. This homology of this gigantic complex, okay? And this as a generalizations of the classical Hasse principles, like for quadratic forms and also Hasse principle for the central simple algebra of a number field, Kata proposed the following conjecture. So for X smooth and proper of a finite field, or this is a more arithmetic case, so regular, proper, and flat over the integer ring. For these situations, this also I have to, this is for the simplicity. Also I have to assume this X has no other valued point, okay? So this is a similar condition to the case of the totally imaginary field, okay? And then this Kata homology should vanish, except the degree 0. That's a conjecture. Okay, this is a this is now called like a Kata conjecture or a cohomological Hasse principle for the higher dimensional arithmetic schemes. And then, of course, dimension 1 case is the equivalent to the classical Hasse principle for the central simple algebra of a number field or a function field in one variable of a finite field. This is the classical fact, okay? And then dimension 2 case was done by Kata himself. This was consequence of the some higher dimensional classical theory. So this is sort of the higher dimensional classical theory for X. And another result is a vanishing of the Kata homology up to degree 3, but with infinite coefficient. So, so this is due to Kuryotenen and Swa and also Janssen and myself. And then these are kind of result for low degrees. Then in 2006, some general method to approach to the Kata conjecture for the all degrees was proposed. In the theorems, X is now a smooth project of a finite field, and this Kata homology vanish as desired, either up to degree 4, or if you admit the resolution singularity. Of course, this is not known of a finite field, but this is a conditional result. Then, in 2009, in the joint work with Kurz, we are able to remove this annoying assumption on the resolution singularity. But we have to restrict the prime to p coefficient. So this is current state of art for these Kata conjectures. And also there is some works in progress to show these Kata conjectures for the more arithmetic schemes. I mean schemes flat over integer ring. Yes?
When you were defining the complex, I thought you only did it for prime to p.
No. It's sorry. Yeah. That's a good question. Yes. Yeah. Here I said if this one, but otherwise there's a way to define. There's a way to define it. Yeah. Yes. Thank you. Yeah. Welcome. Welcome to the question. Okay. So this is the current state of art for the Kata conjecture. And actually, so I just said a few words on the key ingredients of the proofs. The first ingredient is this weight argument. So guaranteed by this Durinis proof of the Weil conjecture. And second key ingredient is a recent result by Gabas on the refinement of the Duyong's alteration. So this second ingredient kind of enables us to remove the resolution singularity. Okay, but prime to p, because Gabas result works only for prime to p part. Okay, so now application to the motific homology groups. But maybe, because maybe I suppose not everybody in this room is familiar to the motif cohomology groups, I just like to make some brief introduction to the motif cohomology groups. And then for this, I'd like to start with the classical fact, again, classical fact of the number theory, okay? Class number formula. So we look at this Dedekind-Zenz functions of number field, and then we are now interested in this special value at s equals 0, okay? So now rho 0 is the order of s at s equals 0 of the Dedekind-Zenz functions, and which is known to, this is known to be fact, I mean, which is known to be rank of the unit group of the integer ring of this number field, okay? But this is a well-known fact. Then this class number formula reads as follows. So this equalizes these numbers to these quantities. Here, this guy is ideal class group of the number field. And this guy, of course, this is a torsion part of the unit group, which means like a group of the roots of unity, okay? And this Rk is so-called a Dirichlet's regulator. So that's class number formula. Then in order to motivate the introduce motivic cohomology groups, we ask the following question. Can we view this formula as the sort of arithmetic index theorem? Which means, which equalize some analytic invariant called the index to the some topological invariant characteristic class. It's like a Euler-Poincare characteristic. And for this, we have enters the motif cohomology enters in the picture. So this things is defined for schemes with appropriate condition. We have some Abelian group associated. And then you have two indices, like one is the degrees of the cohomologies, and another is the weight of the cohomology. Okay? And for example, if X is a spectrum of the integer ring with the number field, first cohomology with weight 1 is a unit group of the integer ring. Okay? And the second one is the ideal class group. And other things vanishes for the weight 1. This is for weight 1. Okay? So, this classical class number formula now reads like this. So this equalizes the zeta values with this like a sort of some part which sort of looks like a Euler-Poincare characteristic. But we have some another term like called regulator. But I will come to this again later. But anyway, so this is sort of the motivation to introduce motivic cohomology groups. And I just give you some very, very brief construction of the motivic cohomology groups. There are two ways to construct it. The first one is due to Voevodsky's. So we consider the category of the smooth schemes of a fixed ground field K. Okay? And he constructed the triangulated category of mixed motifs of a K. Whatever it is, some sort of category with some very nice properties. And then this is equipped with some functor from this category to here, which means like for each smooth scheme X over K, you have associated mixed motifs. Okay? Then this motivic cohomology group is defined as Hom set from this motif associated to X to some special, very special object called a Tate object in this category. So that's the very, very somehow beautiful, you know, like very beautiful machinery to define this motivic cohomology groups. But there are a second construction which is more suitable to the computation. So this is given by so-called Bloch's higher Char groups. So this is defined over more general schemes. The previous one is only for smooth over field, but now this is any schemes of finite type over field or even over Dedekind rings. Spencer Bloch defined this so-called Bloch's higher Char group, which is generalization of the Char groups of the absolute cycles modulo rational equivalence. So Q equals 0 case is a usual Char group. Okay? This is defined as a homology of so-called cycle complex, which is algebraic analog of the singular complex in topology. And for the singular complex in topology, you recall that this is the free, so each term is given by the free abelian group over the set of the continuous map from the topological standard simplex into topological space, right? But instead of this, we use algebraic cycles. So instead of the continuous map from the topological simplex, we use algebraic cycles on the product. And here, this is algebraic analog of the topological simplex. Okay? And then we have a comparison theorems with the Voivodski, which equalize the motific homology groups defined by Voivodskis is equal to the higher Char. Okay. That's the introduction to motific homology group. Okay? Now then, why, cohomological Hasse principle, how cohomological Hasse principle is related to the motific homology groups. This is given by the following lemma. So for X regular of finite type over Fp over integer ring, in a d dimension, we have sort of cycle class map from the motific homology group to the etaric homology group. And here again, n doesn't have to be invertible X. So if in that case, you have to take serious care on this coefficient here. So I mean, usually this is a Tate twist, but if n is not invertible on X, you have to take very special care on this, but I don't go into this story. But anyway, this is defined as etaric homology. And etaric homology has been intensively studied. So you have much knowledge about it. But you have cycle class map from the motific homology group. This is sort of very kind of unknown things, still in the mystery. But we have at least some cycle map relating motific homology groups, these mysterious things, to the etaric homology, which is sort of well known. And this kernel and co-kernel is now controlled by Kata homology, like this. Okay? So, I mean, somehow Kata homology gives us some clue to control this mysterious kind of object by some well-known object as etaric homology. Okay? For example, we know etaric homology is finite group. Okay? So that means if you know the Kato's Hasse principle, we are able to give some affirmative result on the so-called finiteness conjecture motific homology groups, which reads as follows. So conjecture is as follows. So X regular of finite type over finite field or integer ring, then this motific homology group should be finite generated. So this conjecture is vast generalization of the finite result on the ideal class group of the number field or unit. So this is Minkowski. So this is due to Dirichlet's. Yeah, this finite generation of the unit group of the number field, and also rational point of the abelian varieties of a number field. So this is the model Bell. So this is sort of the very somehow like ideal kind of conjectures to be shown in arithmetic geometry. But Kato conjecture has some application to give some affirmative result on the conjecture. But I don't go into detail on this. And the second application is, of course, special value of the theta function. So now, but we look at a smooth project of a finite field, and we look at this congruous theta function. Okay, and we are now interested in this special value of this guy. And the known facts due to Grothendieck and Turin and Milun is the following. First of all, this value is rational. The second one, this value is expressed by using this etaric homology. Now we like to relate this value to the motific homology group. Okay? And here's the theorem, which is the consequence of the previous theorem of the Carrots and myself. And so X is smooth project of a finite field. and the data dimension, then we show this torsion part, at least torsion part, of the motific Cohomology group where D is finite group, but modular P torsion. Okay? So this is a new finiteness result on the motific Cohomology group. Okay? And this zeta value at S equals 0 is expressed as an alternating product of the cardinality of these things. Okay? After P power. But up to dimension 4, we can show these things even for the P part. But anyway, this result should be compared to the classical class number formula, which looks like this. Okay? Classical number formula somehow express this value at S equals 0 of the dedicated zeta function of the number field in this way. But here you have Dirichlet's regulator term. But here regulator term was necessary because these things here, this group is not torsion. But here we don't have regulator term. The reason is there is some conjecture due to Pershing, which says for the weight of D motific Cohomology for both this smooth project schemes of finite field, this group should be a torsion group. So that's the reason why here we don't need Dirichlet's regulator term. So this makes my life very easy. Okay, so that's application to the special value. Okay. Any questions so far? So that's now part friendly to the number theory is now finished, and then we come to the part for the algebraic geometers. So now we come to the application of the singularities. So there are two singularities, two kinds of singularities which can be somehow studied by as application of the cohomological Hasse principle. So one is a cosine singularity. Okay, and so let's take the finite group, which acts linearly on the n-dimensional fine space. Okay, and we form the quotient, geometric quotient, which may have some singularity. And we resolve the singularity. Okay, but in a good way. There are many ways to resolve the singularity, but you have to choose some good way to resolve the singularities. And then we look at the exceptional divisor, which we assumed a simple normal crossing divisor. So this is now this is a singular locus of this quotient, and we take the inverse image by this map, resolutions, and we take a reduced part. Okay, then we assume this is simple normal crossing divisor on this y. Okay, then we were interested in configuration of this exceptional divisor, which means this is a topological simplicial complex whose asymplicity is A plus 1/4 intersections of the irreducible components of the exceptional divisor. Okay? So we are now interested in how this exceptional divisor configurate, right? How do they, all this irreducible component intersect each other. So this is somehow like problems which has been studied a long time in algebraic geometries. Indeed, this pi 0, pi naught means set of the connected component. So this is a set of the connected component. Sorry, connected component set of the connected component of the A plus 1/4 intersection of the irreducible component of the exceptional divisor E. Okay, that's a definition. Okay, and then actually the two-dimensional case. This was a very classical problems studied by Klein. This is so-called Klein singularity. Okay, and then So in this case, we know this origin is isolated singularity. Okay. In a higher dimensional case, we don't know. We don't know this is isolated singularity, but in a two-dimensional case, so X, we record that X is a two-dimensional fine space, and G acts on it linearly. We form the quotient, and the singularity is now isolated. Okay, and also this case is G is easily classified into the cyclic case, binary dihedral, and also some groups corresponding to the Platonic solid. So this is the very classical things. And for example, let's look at the binary dihedral case. So G is now given by these generators and the relations, and then this quotient is now hypersingularities, given like this. Okay, and so with this concrete equation, it's easy to resolve the singularities. And exceptional divisor now looks like this. So all components are P1, and I guess there are, I think, n plus 2 components. And only at last step, you have 2 components intersecting this previous component. And so configuration complex for this, given by this linking diagram. Okay? So that's the concrete, this is a consequence of the very concrete calculations. But in general, still in case, still we are in a two-dimensional case, but for general G, okay, Mackay gave some key, very nice observation that this configuration complex, and this is still in two-dimensional case, is computed as so-called Mackay graph or Mackay quiver, which is determined by just in terms of the irreducible representation of this finite group G. So somehow, configurations of the exceptional divisor of the quotient of affine space by finite group G is mysteriously computed just in terms of the representation of this group G. That's an observation by Mackay. Okay? But unfortunately, of course, this was the starting point of this so-called theory of the Mackay correspondence. So people has been trying to generalize this fact to the higher dimensional case. But unfortunately, at this moment, so no general theory has been established. To extend this Mackay's observations to the higher dimensional case, okay, except the toric case. So this is maybe too difficult question for me.
I'm sorry.
Yes?
This gamma E was this configuration graph of the...
Yeah, configuration graph of the exceptional, yes.
So how does this depend on your choice of resolution?
Yes. It depends. So that's why I said the good resolution. You have to choose good resolution.
Oh, this Crepin resolution?
Yeah, Crepin resolution. Yes, Crepin resolution. Yes. Right, and then of course, so gamma E itself depends on the resolutions. Okay, and you have to choose a resolution to somehow to say something about the gamma E. Okay, now so this is maybe too difficult for me. So now I compromise to look at the homology of the complex. Okay, let's see. Previous case. So this is 3. So no homology. This is homologically trivial, or this is even contractible. Okay. So how about the higher dimensional case? That's my question now. Can we compute somehow the homology of the configuration complex? That's my question now. Okay. So this homology is by definition given by the homology of the complex like this. So free degree A term is just a free abelian group on the set of the connected component of the A plus 1 fold intersection of the irreducible components. Okay, you have this complex here. This is now a complex of abelian groups, and we have to compute the homology of these things. Okay, so now result. which is consequence of the cohomological Hasse principle. Okay, this is a little bit surprising because cohomological Hasse principles for the something for the arithmetic schemes. But now we are now we can talk about some result over general field now. Okay, but anyway, so we take any field K and P is exponential characteristic, and then you take quasi-project smooth varieties over K acted by some finite group. Okay, and you form the quotient, and that V is a singular locus of this quotient. Okay, and we assume first of all like Z is smooth and proper. Typical case. We are now thinking a typical case is the isolated singularity. Okay, and second assumption is the existence of the resolution because we are now in a positive characteristic. Maybe positive characteristic. This is not guaranteed. So we assume the existence of the resolution of singularities. So Y is smooth. Suppose the proper birational. Y is smooth, and the exception now is a simple Malcross divisor. Okay, and pi is isomorphism of a regular locus. Okay, that's assumption. And then we like to say something about the homology of the configuration complex of E. Okay, then I have to confess that I need some very annoying, apparently redundant assumption, which is existence of the equivalent compactification, smooth compactification of X. Okay, X was not supposed to be a compact. Okay. Then I can conclude that in the homology vanish, ignoring P torsion. Okay. So there are two issues around this theorem. First of all, I don't know, maybe our method of proof is some defect, but seemingly, this redundant assumption. So this is this assumption concerns somehow resolution of the singularities along the boundary of X. But we like to get some conclusion on the result of singularity of X over G. I don't know, but seemingly from looking at proof, there seems to be a very, very mysterious link between the resolution of this X over G and resolution of the boundary of X. That's our feeling now. Or maybe our method to prove has some defect. But anyway, with this redundant assumption, we can show the vanishing. There also another remark is for P torsion. Actually, we can get stronger conclusion which says vanishings even including P torsion, assuming more stronger resolution singularity. But anyway, I'll come to this later. Also another point is in characteristic zero. This conclusion is not so surprising because in characteristic zero, actually this singularity is not so bad. This is just a quotient singularity, and this is now what? Rational singularity. Therefore, rational singularities, there is a way to show the vanishing of this homology of the configuration complex, but with rational coefficient. You have to ignore the torsion part by using Hodge theory. So there is another way to show this rationally. Okay, but in positive characteristic, this conclusion seems a little bit surprising because G could be P group, and then this singularities of this quotient could be very nasty. And for such as nasty singularities, and I don't see, or I ask some experts in the resolution of singularities, we don't see any geometric reason why this homology configuration complex is of the configuration complex for the exceptional divisor is homologically trivial. We don't know any purely geometric way to explain this. Yes?
Zero. When you say
Weight argument, yes.
So then why isn't there that kind of a weight argument in characteristic P?
Yes. Yeah, maybe rationally. Rationally. But I think, let me think. I see. Rationally, maybe rationally possible. Yeah, same. Yeah. And now here, when we come to the more serious singularities, radical singularities. So this is very special to the positive characteristic. And then, so for the simplicity, we assume K is perfect. And we look at the polynomial ring and a variable, and look at the maximum ideal, and look at the generalization of the localization of this polynomial ring at M. So this ring looks like this. So this is sort of a formal neighborhood of the n-dimensional affine space at the origin. So we are looking at formal neighborhood of the affine space at the origin. And so this is the formal neighborhood of the affine space. And we look at this finite radical surjective morphism given by this equation. This is a purely inseparable equation. Okay, so this is very special to the characteristic P. Okay, so alpha is in a square of maximal ideal. So that means this is singular. This cannot be smooth now anymore. So this is a singular scheme. So we are now interested in these singularities. So this we call radical singularities, and we look at this in a singularity, this local, sort of local singularity like this. And then for this, we like to say something about confidential complex, homology of it for the reducible singularity. So here's the result. So this is a very important singularity in the reducible positive characteristic. So now, here's the result. Again, consequence of the cohomological Hasse principle. And this is, so we now assume, so this is not serious assumption. We assume this is isolated singularity. Okay? And then we assume, again, we have to assume reducible singularity, existence of the reducible singularities because we are in a positive characteristic. This is not guaranteed. So this is not proper birational, and this is externalized regular, and isomorphism of a regular locus, and exceptional is a simple normal cross divisor. Okay? And we like to say something about this homology of the confidential complex of E. Again, very similar to the previous theorems, we need, again, redundant assumption, apparently redundant assumption, which looks like this. So we are given formal neighborhood, the affine space at origins, and this is some local singularities given by purely inseparable equations, and we are given some resolution of it, okay? And redundant assumption is the existence of the globalization of these things, which means, so U and V tilde and smooth and projective, these global things, and V is integral projective, and these are all Cartesian diagram, and U, so you are given some point of U whose formal neighborhood is just given by this guy. Okay? So this kind of assumption of the existence of the globalization of this resolution singularity of the local singularities is required to get a conclusion like this. So somehow this annoying kind of puzzling situation is very similar to the previous theorem. We like to get some information about the configuration complex of the resolution of the local singularity. But for this, we need somehow resolve the singularity of the boundary of this local singularity. Here, again, some mysterious link between the resolution singularities of the local singularities and the resolution singularity of the boundary of these local singularities is indicated. Okay? Yes?
But with your assumption on X and X tilde, are there situations where you don't have a globalization?
I started from the some local resolution. X is very local things. Yeah? But, I mean, in a positive characteristic, of course, I mean, you don't have even, you don't know if even this U exists. You don't know. You don't know. Yeah. You have to somehow smoothly compactify. Yeah? And also, you don't know, of course, you don't know the resolution of it. Okay, so this involves the resolution singularity of, first of all, compactifications, and also like you somehow pull back this guy U to the head here by purely inseparable extension. Okay? And then again, new singularity may appear along the boundary. Then you have to resolve it again. So there are many two steps of the resolution singularity involved here.
So even this resolution of singularity, this may not exist, even if you assume resolution of singularity.
That's, it exists, yeah. So that's something I'm going to talk about. So this condition, is of course guaranteed by this, some expected statement of resolution singularity. Of course, I mean, so let's formulate it. So this is RSN means like for any integral of dimension less than or equal to n over k, you have resolution singularity like this. Okay. Of course, this is something everybody expects, right? I mean, if you admit, then of course this seemingly redundant assumption is guaranteed. Okay. But here again, I have to say, this conclusion is a bit too surprising, or too strong even. Because I also talked to some experts, and you see, we started from this particular equation. This is very this is the singularity given by very concrete equation. So you can do something about it, okay? You can blow it up. So anyway, you blow it up, okay? And upstairs, you have the exceptional divisor, and there, I mean, new singularity may appear, okay? And if you do just, like if you have some expense of the calculation like this, you feel it's almost impossible to control what kind of a new equation appear to define the new singularities in upstairs. It's very, very chaotic, and it's very seems almost impossible to control the equation, form of the equations to appearing to define the new singularities. Okay? So it's somehow, again here, I mean, this conclusion is again, it's at this moment, I have to say, surprising. And I talked to many, many experts, but nobody could give me any reason why this should be true in a geometric reason. Okay, so now this situation somehow seduced me to introduce a following definition. So this radical singularities is called Medusa singularities if the first and second condition. So first one is this is not serious, this is just isolated singularity. Second one is the existence of the resolution of the local singularity. But this homology doesn't vanish. Okay, then conclusion is the existence of such a singularity disproves the resolution of singularity. Okay, I think everybody knows Medusa, but why Medusa? Because I said, I mean, somehow this Medusa singularities, okay, this guy frees the singularities along the boundary so that this singularity as a boundary cannot be moved, anymore resolved. So this reminds me of this figure. So this figure from the Greek mythology. So gazing upon her, the turns onlooker to the stone. But anyway, this theorem says there's some mysterious link between reducible singularity of the local singularities, like this, and the reducible singularity of the boundary of it. And again, I have to say, this annoying P torsion phenomena also can be somehow treated by assuming stronger reduced singularity, which I talk about now. Okay, still 8 minutes. So I define the quasi reduced singularities. So this is now again isolated singularities and the existence of local singularity and non-vanishing of the honest homology of the computational complex. So it could be a p-torsion group. Okay. Then theorem is the existence of such a singularities disproves the previous reduction singularities or embedded reduction singularity. So here embedded reduction singularity means so any regular of dimension less than or equal to n and any proper closed subscheme, you can resolve the singularities of W in such a way that total inverse image of W becomes simple normal closed divisor. This is so-called like embedded resolution of the singularity. Okay, so this this weaker condition, existence of quasi singularities, reduced singularity, anyway disproved the reduced singularities in some sense. Okay, okay. In the last 7 minutes, why cohomological Hasse principle, such things as some it's kind of arithmetic things related to the this weight homology of the configuration complex. So that's something I'm going to explain. Because so far previous theorems statements are purely geometric, but the Kata homology was a very arithmetic object. So I have to explain this. So let's consider the scheme of separated infinite type over the field. And then, for the computation of these things, we can reduce us to the situation where K is finite generated over prime field. Okay, so that's easy. And then we define variant or some extension, extend the Kata homology. Kata homology was defined for arithmetic scheme. For example, like a schemes over finite field. Okay, but we extend this, this Kata homology to the schemes lying here over finite generated field. That's the first step. Okay, then we prove this cohomological Hasse principle for this extended Kata homology. So that's a theorem. So for the extended Kata homology, we show the vanishing of the Kata homology. Okay? So this is again possible by the same method because we assume the base field is finite generated. So then by this assumption, we can use weight argument again. Okay? Well, for the weight argument, base field doesn't have to be finite. Maybe finite generated over prime field. With this assumption, we can use weight argument and Weil conjecture proved by Drewing. Okay, so that's the first step. Then, second key ingredient is a descent property for the Kata homology, which means for some hypercovering, this is the hyperenvelope means some very special kind of hypercovering. So this is a simplicial object. So hypercovering, some special type of the hypercovering, we have some spectral sequence like this for the extended Kata homology. Okay, so this is sort of a descent property for the Kata homology. Then, for this was observed by first Green for the for his work to defining Hodge structures from the cohomology of the complex singular complex varieties. Then with this properties plus previous result on the Hasse principle for the extended Kata homology, one can show the for this simple normal crossing divisor of E, this homology of the configuration complex is computed by using this extended Kata homology. So our problems on the homology of the configuration complex is now transformed into the problems about Kata homology. Okay? Okay. Then for example, last result on radical singularities follows from the following theorems on the Kata homology. So if you're given some finite radical surjective morphism, this induces isomorphism of the Kata homology. So that's somehow using this, we can show the previous theorem. Okay. Okay, maybe I stop here. Thank you very much.
Any question?
Yes? No, boundary, I didn't care about the configuration of the resolution of the boundary. I just, yes. Yeah. No, I somehow, yes, of course, in the proof it shows up. In the configurations of the boundary shows up in the proof. Yeah, in the proof it shows up. No, boundary it doesn't have, it may have non-trivial homology. Boundary, we cannot say anything about the homology of the boundary. Yeah. Yeah? That I didn't know. I mean, I see. Even in the positive characteristic? No. Oh, I see. I don't know. I mean, seemingly in the positive characteristic, I don't know. I mean, if such some duality exists for the configurations on the centers and the configuration of the resolution of the exception divisor around the boundary. I don't see it. Yeah. I don't see it. Yeah. I didn't know. Maybe I have to learn this. Yeah. In characteristic 0, it exists. I see. Huh? Special case. Okay. Yes?
Do you anticipate the breakdown of resolution similarity?
No. Yeah, I mean, we plan with some people. I have some plan to start some project if either to find the Medusa singularity or to find some purely geometric way to explain why it doesn't exist. I mean, either is true. I mean, of course, Medusa singularity may be just crap. I mean, just like just illusions. But in that case, at least, I think we have to be really serious about finding the reason, geometric reason why it doesn't exist. Yeah, I think so. Yeah.
This is the precious project.
Huh?
The precious project.
Yeah, thank you. Yeah.
Okay, any further question?
How about your result of Medusa?
Kazu Medusa? Yes, I think Kazu Medusa, I think somehow like maybe Kazu, I mean, if something like it exists, maybe Kazu Medusa could be possible. I mean,
Your result does it hold for characteristic view?
no, characteristic P. I mean, this we are dealing with a very special. So this singularity is given by some equation y to the p to the y to the p minus something. So this is very special to the characteristic P. Okay, and then somehow maybe starting point of just look at the characteristic 2. And there you just pick up some very special equations, y to the p, y square minus something, and you resolve it, and try to see if this homology vanish or not. That's all. So this is a very durable computation, and it's really fun to see it. I mean, if this kind of things is true or not. And if it's not true, I mean, if this doesn't exist, I really like to see why this doesn't exist by geometric way. So this is a very long detour, right? I mean, we use a very conjecture to show this result. But statement itself is very purely geometric. And so, I mean, you see this, so I mean, this is a very long detour to show this kind of a statement. So then we have to see some geometric way to explain this.
Okay, let's thank the speaker.
Okay.
Next talk will start in 15 minutes.